Hello and welcome to Beginning Engineers. Today I'm going to be talking about a fundamental concept in electrical engineering, Ohm's law, which is pretty much the basic rule for the world of electricity. So let's start with what is electricity really? Electricity is the presence and flow of an electric charge. Electric charges can be positive or negative. Electricity charge matter produces electric fields, and the most familiar carriers of an electric charge are electrons and protons. So all the wires and cords in your house, those are carrying electrons. So electricity is a very active, moving, positive or negative thing with many types of fields. Electricity has several ways to be measured and defined. Here are a few of the more common ones. Current is a flow of electric charge, electrons, measured in amperes, also called amps. Resistance is the measure of difficulty in passing an electric current through a conductor, measured in ohms. Voltage is the difference in electric potential energy between 2 points per unit electrical charge. It is measured in volts. Let's look at Ohm's law and apply it to a very basic series circuit. So Ohm's law was first discovered and written down by Georg Ohm, a German, in 1827. I may be butchering that first name. The basic rule is current equals voltage divided by resistance. Voltage equals current times resistance, and resistance equals voltage divided by current. So algebraically, you can arrange the equation however you would like. That image of the triangle is very common. So voltage on top, current and resistance on the bottom. They are all related to each other mathematically. A series circuit is one of the most basic types. If a circuit is in series, that just means there is only one singular path for the electricity to flow on. So look at the picture in the bottom left. The total current of the circuit is 25 amps. There's one resistor that has 10 ohms of resistance. So what would the voltage of the circuit be? If you measured across the positive and negative nodes, what would be the voltage of the total system? Well, because we know voltage equals current times resistance, thanks to Ohm's law, voltage would be 25 amps times 10 ohms, so 250 volts. That may sound like a lot, and that's because it is a lot of volts. In typical electrical systems, current is usually in milliamps, not full amps. Full amps could really kill people, but only if there's some voltage with it. So usually with electricity, you need a combination of high amps and high voltage, or a little bit of both to really do some damage. So in the series circuit example, we could have just as easily solved for current or resistance if we had the other two, just using simple algebra. What if there are multiple paths for electricity to follow? Well, that is what you call a parallel circuit. So a parallel circuit is one in which there is more than one path for current to flow through. Things can get a lot more complicated. But there are some basic rules that can help us solve these circuits. Voltage will be the same across each component in a parallel circuit, so that's a bit different than a series circuit. But current, on the other hand, which is constant in a series circuit, will vary in a parallel circuit. And sometimes they say, think of electricity like it's water. So you have all these branching paths. The flow of water isn't always going to be the same on each path. Just like rivers in real life, some streams that come off of it are going to have more flow, others are going to have less. Same thing with current in a parallel circuit. One thing that really helps with splitting off currents is that the sum of the currents on every single path will equal the total current that's coming from the power source. So looking at our picture, if we had 6 amps of current coming from the power source and 3 separate paths for that current to go on, if each path had the same resistance to flow, then each path would have 2 amps of current flowing through it. But what if each path didn't have the same resistance? Well, that's when we have to use the total resistance formula to solve for the total resistance or individual resistances. This can then be extrapolated to each path to solve for the different current flows in each path. So the total resistance formula goes like this. 1 over the total resistance equals 1 over each individual resistance added together separately. So 1 over the resistance of the first resistor plus 1 over the resistance of the second resistor, so on and so on, will add up to be 1 over the total resistance. So the math here can get a little tricky, but let's walk through an example. So say that we know the total resistance of the circuit is 30 ohms. We know that on the first resistor, the first path, the resistance is 50 ohms. On the second resistor, second path, it's 100 ohms. So what would the resistance be on the third resistor, the third path? Well, we would take our equation, 1 over the total would be 1 over 30 ohms, which is 0.033, is equal to 1 over 50 plus 1 over 100 plus 1 over x. That 50 and 100 are the values of each resistor, the resistance in each path. So 0.033 equals 0.02 plus 0.01 plus 1 over x. Subtract the 0.02 and 0.01 to the other side, basic algebra. We're left with 0.003 equals 1 over x. From there, we get that x must be 300. So the third resistance, the third path, has 300 ohms of resistance. Now that we know all the individual path resistances, we can solve for the current on each path. So we know the total current would be 12 volts divided by 30 ohms. So that would be 0.4 amps, also known as 400 milliamps. So the path 1 current, using the same Ohm's law, the same equation, 12 volts divided by 50 ohms, 0.24 amps. Path 2 would be 12 volts divided by 100 ohms, 0.12 amps. And path 3 would be 12 volts divided by 300 ohms, 0.04 amps. Now it's always 12 volts because this is a parallel circuit and the voltage would be the same. But as you can see, the currents differ. But they all add to be the total current of the system. You can include another unit of measurement for electricity called power into Ohm's law, but this will change the diagram, so it won't make intuitive sense anymore, kind of like the triangle did. The triangle, whatever one you wanted to solve for, you just looked at the other two and whatever their position was to each other, and that would tell you how the math worked, whether it was multiplying or dividing. If you include power, it becomes a wheel, although this diagram is useful too because it does have all the equations laid out. So power is just voltage times current, and sometimes voltage is represented with an E, not always a V. What's useful about this is that you can use power to solve for resistance, current, or volts. So if for some reason you have power but not something else, you could use one of those equations to figure it out. Alright, I'll end on some additional items I want to briefly describe, because I think if you're talking about electricity, circuits, devices, things like that, you're going to hear some of these terms thrown around. So first of all, you have a diode, which is an electronic device that only allows electricity to flow in one direction. So that's pretty interesting. If you try to go one way in the diode, the resistance is almost infinity, whereas the other way, it's pretty much zero. So it makes it really enticing for electricity to just flow one way. You have a certain type of diode called a rectifier diode. This converts alternating current to direct current. And alternating current is just current that changes, usually modeled with a sine wave. Alternating current is called AC, and it's what our houses use, businesses use. We don't use direct current. You have capacitors, which temporarily store electrical energy in an electric field. Think of a battery. They're very similar to batteries. You have inductors, which are also known as coils or reactors. They are devices that resist the change in an electrical current by using magnetic fields. They can block AC and only allow DC through. This is called choking. Capacitors, resistors, and inductors are the three passive linear circuit elements. So those are the main three you hear talked about a lot. Just a fun fact, if it's kind of hard to grasp this concept, just in the real world and practical sense, many dials and tuners on devices are connected to either a capacitor, an inductor, or a reactor. So you're changing some property of the circuit, and it's literally affecting the output you're getting. Whether you're changing the current, the resistance, or the voltage, it's going to have an end effect on the electrical flow. You also have digital logic gates, which are most of the images on the right side. That gets into newer stuff that's a little complicated and outside the scope of this video, so I won't bother with that. But just so you have an idea, logic gates kind of say, there's four different possibilities. If these two are correct, we let something through. If not, we don't. That's kind of the basic concept. And then on the right are all the images of the things I talked about and how they would look on an electrical diagram. If you enjoyed this video, please subscribe. Thank you so much for watching. I'll try to do a few of these a week. At least for this summer, anyway. I'll try to cover a variety of topics as well, but hopefully now you know a little bit more about Ohm's law and some basic electrical properties and equipment.